Hi everyone. So this is example 2 of the simplex method. So in this I'll try to minimize this objective function. This is 3x1 plus 4x2 subject to these three constraints, with x1 x2 being non-negative. So here we can see that two of the constraints are less than equals to type, but one of them is greater than equals to type. So this calls for an artificial variable. So for these type of problems, what we try to do, we use two-phase simplex method. So we try to start with simplex phase 1. So the first thing that we do, we add slack and artificial variables. x3 is the slack, x4 is the slack, x5 is the slack, and x6 is the artificial variable that we are going to add to this problem. So in the phase 1, what we'll try to do, we'll try to minimize this z star equals to x6 subject to these three constraints and the necessary non-negativity constraints x2, x3, x4, x5 and x6 has to be greater than equals to 0. This is mandatory. So now what happens, we try to create the simplex tabulo. So simplex tabulo will have number of rows equals to number of constraints, so 1, 2 and 3, and we just rewrite all these constraints in the tabular form. So this becomes 3x1 2x2 plus x3 equals to 12. This is the first constraint. x1 plus 2x2 plus x4 equals to 6. This is the second constraint. Then 2x1 minus 7x2 minus x5 plus x6 equals to 10. So now calculating dou f by dou xk using this CB and CT, we'll get, so the first term becomes 0 minus 3 into 0 minus 1 into 0 minus 2 into 1. So this becomes minus 2. Similarly for the second term, 0 minus 2 into 0 minus 2 into 0 minus minus becomes plus, so plus 7 into 1. So this becomes 7. Similarly doing for all the remaining terms, we will get this. So we need to select the most negative. So here the most negative is this. So this will be the entry variable. I am going a little bit fast because I have explained all these things in the previous video. So in that example we were discussing about an unbounded problem. So now continuing here, so what we will do, now entry variable is decided. So now we go to bj and divide all the terms of bj with the corresponding column of the entry variables. So 12 divided by 3, 6 divided by 1, 10 divided by 2. So we will be getting these values. Now we select the least positive. So the least positive is 4. So this becomes the exit variable. Alright. So we create the next tabulo. So earlier this was 3 and we want to make it 1. So what we do, we instead of r1 we take r1 by 3. So all these terms take the corresponding values. So this becomes 2 by 3, 1 by 3, 0, 0, 0 and 4. Now earlier this was 1 and now we want to make it 0. So now what we do, r2 will be transforming with r2 minus r1. So we'll be getting all these values. Please note that this r1 is the updated r1 after this. Now for the second term, earlier it was 2, now we want it to be 0. So we will do r3 equals to r3 minus 2 times r1. So we'll be getting all these values. Now following the same process, we calculate dou f by dou xk. Now calculating dou f by dou xk, 0 minus 1 times 0 minus 0 times 0 minus 0 times 1, so this becomes 0. Now for the second term, so 0 minus 2 by 3 into 0, 4 by 3 into 0, and minus 25 by 3 into 1, so this becomes 25 by 3. Now following the same process, this will become 2 by 3, 0, 1 and 0. Please note that all these dou f by dou xk are greater than or equals to 0. All of them. Dou f by dou xk are greater than or equals to 0. So this means that this point has to be an optimal point. Now at optimal point, we see that x6 is still in the basic variables. So whenever we are doing phase 1 of simplex method, like whenever we have greater than or equals to constraints and we add an artificial variable and we try to solve an initial simplex problem by minimizing that artificial variable, if that artificial variable remains in the basis even after the optimal solution has reached, so we have to conclude that this solution has no feasible point. So the given linear programming problem has to be infeasible. Okay, thank you.